Alright everyone, we're going to go ahead and get started. So today we're going to talk about, continue talking about partial derivatives, start tangent planes and linear approximations. We're going to discuss differentiability of functions that map R2 to R, and we're going to start the chain rule. So we left off with a little bit of calculation of first partial derivatives of functions of multiple variables. So let's do an example. We have a function w. W is a function of z, x, and y, defined by z times e to the xyz. So if we want to calculate all the partials, but specifically the partial of w with respect to x, this is just going to be, let's see, z, because that's a constant with respect to x. And then we copy paste, and then the derivative of the inside, well, this is x to the first, so we just have a yz. So this is yz squared e to the xyz. Same situation for y. This is going to be, it's going to be xz squared e to the xyz. But when we take the partial of w with respect to z, we'll notice that we have z times e to something with z in it, so we need the product rule. The product rule, we have the first times the derivative of the second. The derivative of the second will be xy e to the xyz. And we have plus the second times the derivative of the first. The derivative of z with respect to z is just 1, so we have just e to the xyz. This is equal to, let's factor out an e to the xyz, and we're left with xyz plus 1. Okay. Now if we have a function f of xyz equals, it's going to be a polynomial this time. We have xz minus 5x squared y cubed z to the fourth. This is not scrolled down. So if we want the partial of f in respect to x of xyz, this is just, you can write it shorthand f sub x. This is going to be z minus 10xy cubed z to the fourth. The partial f respect to y, we just write it as f sub y is equal to, well, this first term is just a constant with respect to y. And then the next one we have a y cubed, everything else is constant. So we have negative 5 times 3, negative 15 x squared, y squared, z to the fourth. And then we have partial of f respect to z. For the first term, the z goes away. Now we just have the constant x. Then differentiating the second term, we have a z to the fourth. So we have negative 5 times 4 will be negative 20 x squared, y cubed, z cubed. Okay. Now we have a function. This is the third one. So we have mu equals, this is e to the r times theta times sine of theta. And we no longer want the first partials. We want the third partial of u respect to r twice, respect to theta. Now, reading this, well, which partial should we take first? Which partial we should take first would be to do theta first, and then travel this way, do 2r's. You always read it from right to left with these partials because, if we had, say function is we say f is a function of x, y, and then let's say we first take the partial respect to x of f of x, y. So this would be the partial of f respect to x comma y. But then we do the partial of y of this new function, the partial of f respect to x of x, y. Well, you see, this is now on the left-hand side, and partial of x, which we did first, is on the right-hand side. We have two partials on top. We have f, and we have partial y respect to x. So this is actually the partial of f with respect to x first, and then with respect to y. So that's how we're going to proceed with this example. We're going to do theta first, and then we're going to differentiate with respect to r twice. To differentiate with respect to theta and get partial of u with respect to theta, we need the product rule. See the first times the derivative of the second plus the second times the derivative of the first. Let's see, we can factor out an e to the r theta. We're left over with cosine theta plus sine theta times r. Okay, now we need to take partial respect to r of the partial of u with respect to theta. Okay, so now we need the product rule. Let's see. Okay, so we have the first times the derivative of the second. Well, the derivative of cosine theta is just 0 with respect to r. And then the derivative of sine theta times r would just be sine theta, because with respect to r to the first. Then we add the second times the derivative of the first. Well, the derivative of the first with respect to r would be theta e to the r theta. We just copy and paste. Okay. So this is the partial squared of u with respect to r with respect to theta is equal to this guy. And so we're just going to take the partial with respect to r of the partial squared of u with respect to r with respect to theta. So with this first term, differentiating this with respect to r, we get theta e to the r theta times sine of theta. The second term with respect to r, we need the product rule. And so we would get, with respect to r, the first times the derivative of the second plus the second times the derivative of the first with respect to r will be theta squared e to the r theta. Okay, so I have a theta in every term, I have an e to the r theta in every term. I'm going to factor that out. Then I have a sine, another sine, so this is 2 sine theta. And then we have plus theta cosine theta plus theta r sine theta. And that is the third partial of u with respect to r twice in respect to theta. Okay. Now we're going to talk about, well, we're going to verify some partial differential equations, which is just going to be an exercise in taking partial derivatives. So a partial differential equation is an equation involving partial derivatives of a function. Okay, so we have the question: does the function u is equal to ln the square root of x squared plus y squared, does this function satisfy Laplace's equation? Laplace's equation is given by u sub xx plus u sub yy equals 0. So we need to calculate the second partial of u with respect to x twice, and then the second partial of u with respect to y. Add them and see if it equals 0. So taking the first partial u with respect to x, we get one over the square root of x plus y squared, and then the derivative of the inside, well, this would be 1/2 x plus y squared to the negative 1/2 times 2x. So this is really, well, the 2's cancel. We have x over x squared plus y squared. We need u sub xx. U sub xx, we need the quotient rule now. Y is constant, u is the variable we're differentiating with respect to. So then we have low, b high, well, the derivative of the top is just 1, minus high b low over the square of what's below. Okay, so this is actually going to be y squared minus x squared over x squared plus y squared squared. And now we need to calculate the second partial of u with respect to y. So uy would be, well, that would just be y over x squared plus y squared. We have u sub yy would be, well, that would be low d high minus high d low over the square of what's below. So this would be x squared minus y squared over x squared plus y squared squared. Adding these two, uxx plus uyy, we get y squared minus x squared over x squared plus y squared squared plus x squared minus y squared over x squared plus y squared squared. We have a common denominator, so we can add, well, we have a negative x squared, positive x squared, positive y squared, negative y squared. Is this equal to 0? So we verified that u does satisfy Laplace's equation. Okay. We have another equation. We have an equation, let's see, it's going to be z is equal to the natural log e to the x plus e to the y. It says verify that this is a solution to the partial differential equations, the partial z with respect to x plus the partial z with respect to y is equal to 1. And we're going to do different notation. We have zxx times zyy minus zyx or zxy squared is equal to 0. Okay, so we have the partial, we have z with respect to x is e to the xy, or e to the x plus e to the y. And then e to the y is just a constant with respect to x, so we have e to the x in the numerator. We have zy would be e to the x plus e to the y on top. Adding these two, what do we get? We get e to the x plus e to the y over e to the x plus e to the y. This is equal to 1. Verified. So this next one, let's do zxx. We already calculated zx. We need the quotient rule to calculate zxx. So we have, let's see, low d high minus high d low over the square of what's below. So we have e to the x times e to the x. If the bases are the same, we add the exponents. So e to the 2x plus e to the y plus x minus e to the 2x over e to the x plus e to the y squared. Well, these cancel. This is e to the y plus x over e to the x plus e to the y squared. Now calculating zyy, we have, let's see, we have low d high minus high d low over the square of what's below. Well, that's the same thing, right? Because we have these cancel. Then we have this one, e to the x plus e to the y over e to the x plus e to the y squared. Now we need d sub yx. That's going to be low d high, well, derivative of the top with respect to x is 0, minus high d low with respect to x is just e to the x over the square of what's below. Okay. So we have oh yes. So we have e to the x plus y over e to the x plus e to the y squared times e to the y plus x over e to the x plus e to the y squared minus zyx squared. Zyx squared, well, that's just the same thing as this. We have e to the x plus y, e to the x plus e to the y squared. This is equal to 0. Verified. Okay, so given you're told there exists a function f whose partials are f sub x of xy is equal to x plus 4y and f sub y of xy equals 3x minus y. Should you believe them? Now, to solve this, we're actually going to do some integration. We're going to integrate this function f sub x of xy with respect to x. Get the integral of x plus 4y dx. We treat y as a constant, x is the variable. So then we get x squared over 2 plus 4xy plus g of y. This is my constant of integration because we're integrating a function of multiple variables with respect to x. The constant of integration will be a whole function of y. In a similar manner, f sub y xy dy is equal to the integral 3x minus y dx. So then we get 3xy minus y squared over 2 plus g of xy, or h of xy this time. Now, you may be saying, okay, well, this one has an x squared, and this one has a y squared, so it's not the case. There's no function. But that's actually okay, because when we integrated partial of f with respect to x, we got a constant of integration g. When we integrated f with respect to y, we got a constant of integration h. So this h would be x squared over 2. G would be negative y squared over 2. The problem lies in this 4xy, and this 3xy. Since these are not the same, there is no function that has partial derivatives like this. Okay, now we have tangent planes and linear approximations. So, let's start out with an example, a single variable case. Find equation of tangent line to the curve f of xy equals 3x squared minus 5x plus 8 at x equals 0. What do? We take the partial derivative, or we take the derivative, f prime of x. We get 6x minus 5. Evaluate this at x equals 0. We get negative 5. And then we have our point slope form. Our point slope form is y minus y1 is equal to m times x minus x1. Well, really, let's rearrange this. Let's call this y is equal to f of 0 plus f prime of 0 times x minus 0. Well, f of 0 is really 8. F prime of 0 is negative 5, so we have y is equal to 8 minus 5x. Okay. But now we're dealing with it's really a pain. Where we have a surface S given by a function z is equal to f of xy, and we want the equation of the tangent plane at a point, x naught, y naught, z naught. Now, I didn't realize people were here. Oh my gosh. Okay. Well, cool. So, I don't know why my notifications aren't going off. It's strange. Well, anyways, so I have a pretty picture for y'all. So we have the x, y, z coordinate system. We have some surface. My Cal 3 teacher always told me is like imagine it's a flying bed sheet. this one time he went on this huge tangent about a tint. He compared it to a line integral. He went all out on describing this tint to us. But so we have this surface, and we're gonna call this curve that I drew on the surface. This is the curve of intersection of S with the plane y equals y naught. So we have a plane right here, and then the curve of intersection is this guy, and it passes through a point x naught, z naught, and then we have another curve of intersection with the plane x equals x naught. So we have these two curves, they intersect each other at x naught, y naught, z naught. And so the definition of the tangent plane the plane that contains the tangent lines to C1 and C2. C2 being the curves of intersection. Now really, if I'm not mistaken, we don't actually, it doesn't have to specifically be the curve of intersection with y equals y naught and the curve of intersection with x equals x naught. Really just, two lines, and then who cross at that point, and then their tangent lines being contained on the tangent plane. It doesn't specifically have to be these, but this is just the easiest one to calculate, right? Because you take partial derivatives with respect to x and respect to y all day. So suppose f has continuous partial derivatives. An equation of the tangent plane to the surface z is equal to f of xy at the point P, x, y naught, z naught, is given as follows. So when we're going to calculate a tangent plane, this is what we're going to use. We're going to use z minus z naught is equal to f sub x of x naught, y naught, x minus x naught, plus f sub y, x naught, y naught, y minus y naught. Okay. So we just take the partial derivatives, we evaluate them at the specific point. This is the function value of the surface at the point, and you just plug it in. Now I'm also going to talk about linear approximation. The linearization, how the book gives it, the linearization of a function of two variables will be given by L of xy equals, drum roll, it's the exact same thing. I just wrote it a little bit different. F of AB plus f sub x a x minus a plus f sub y a b y minus b. And this is approximately f of xy when x and y are close to ab. That's the same idea as, you go back up to this tangent line example. If we have some curve and say it's some wacky equation that I can't really evaluate at some point, but we have this equation of a tangent line. We have a function value at this point, but we don't want the function value at this point. Well, we just evaluate it at the tangent line, and it's approximately, if the function is nice enough to us, and if we're close enough to the point, then we get a pretty good approximation. And we're going to do some examples that involve that. go ahead and do that right now, actually. Okay, so let's say we don't have a calculator. We have no calculator, and someone asks us, hey, can you approximate the value of 0.99 times e to the 0.02 to the 8th for me? Well, now we can, because we have this multivariable calculus at our disposal. So actually approximate this number, and when I did this, it was correct within 2 decimal places. So here we go. We got we got some wacky number times e raised to some wacky number, all that raised to the 8th. So I'm going to define a function. I'm going to say f of xy is x e to the y to the 8th. And we're going to evaluate, we're going to do this linearization near the point. Well, x has to be near 1. Y is near 0. So it's going to be at the point 1, 0. And then the y value would be, 1 e to the 0 to the 8th. That's just 1. Cool. So this is f of 1, 0. So we have, what do we need? We need the partials, and then we just need to plug it into this, either, the tangent line, or the tangent plane formula, or this linearization formula. They're the same. So let's calculate the partial of f with respect to x. Well, this is just going to be 8, right? Because this is just 8 x to the 8th e to the 8y. So we have 8 x to the 7th e to the 8y. And we're evaluating this at the point 1, 0. We get 8 times 1 to the 7th e to the 0. So this is just 8. And then we have f y of xy equals, let's see, with differentiating respect to y, we have, this is a constant multiple to x, and then with respect to y, well, the 8 just comes out, then we copy and paste the e to the 8y, evaluate this 1, 0. We have 8 times 1 to the 8th e to the 0. This is 8 again. Now we can, we have everything we need. So I'm going to use the tangent plane formula. So we have z minus z naught, which is 1, is equal to 8 times x minus 1 plus 8 times y minus 0. So this gives us z is equal to, we have 1 plus 8x minus 8 plus 8y. So z is equal to 8x plus 8y minus 7. Okay, now I have something that approximates f near the point 1, 0. So I'm just going to plug in these wacky numbers it gave me initially, the 0.9 and the 0.02 into z, because I can do that by hand. That's just simple arithmetic, right? We have z is equal to 8 times, and x was 0.99 plus 8 times y, which is 0.02. And we have minus 7. Okay, so we have 0.99 times 8. Well, this is 72. 72 plus 7 is 79. Put it over 2 places. So 8 times 0.09 is 7.92. We have 8 times 0.02. This is 16. Move it over 2 decimal places. Plus 0.16 minus 7. Okay, so we have 7 minus 7. We have 7.92 minus 7. So this is just 0.92 plus 0.16 So 0.92 plus 0.16, this would be 8. And then 9 will be the 10. Then move it over. So carry the decimal place down. So this is 1.08, approximately 0.99 e to the 0.02 to the 8th. And you can check using your calculator. It'll be correct to 2 decimal places. So, okay. Let's see. Let's see what we can do now. Okay. Okay. This is a pretty cool example right here. Yeah, this is really annoying. I don't know why it doesn't give me more. Oh, I can do that. Oh my gosh. That just made my life 100 times easier. Okay. Man, that's okay. I just press the down button and it goes down. Who would have thought? Okay, so find the equation of the tangent plane to f of xy equals x squared minus 2xy plus 2y squared. Let's see, having slope 2 in the positive x direction and having slope 4 in the positive y direction. Equation of the tangent plane having slope 2 in the x direction. So we have, this problem is telling us the the value of the partial derivative we need to have. In the x direction, so this is just saying, right, we have f sub x equals 2 and f sub y equals 4. Well, what are we missing from our tangent plane formula? The tangent plane formula was z minus z naught is equal to f sub x, x minus x naught, plus f sub y, y minus y naught. This time we are given the slopes and we have to find the point. So we're going to have to solve some equations. We're going to have to take the partials of f, set them equal to 2 and 4, and find the x and y values that satisfy that. So we have the partial of f respect to x of xy is 2x minus 2y. The partial of f respect to y of xy is going to be, let's see, that's going to be a 4y, I'm doing the last term first, minus 2x. Okay, so we want f sub x to equal 2, f sub y to equal 4. Okay. Ah, cool. Sweet. Okay, so now we have a system of equations. X minus y is equal to 1, because I just took and divided everything by 2. I'm going to rearrange this, divide by 2. So we have, let's see, this is negative x plus 2y is equal to 2. Can I just add these? The x's will cancel, so turn into y is equal to 3. And then I plug in 3, I guess, to the first equation. I have x minus 3 is equal to 1, x is equal to 4. So it happens at the point 4, 3, and let's calculate the f of xy value. So that would be 16 minus 2 times 12 plus 2 times 9. Let's see, 16. So this is 16 minus 24 plus 18. 16 minus 6 is 10. Okay, so we have z is equal to 10 plus 2 times x minus 4 plus 4 times y minus 3. The only things that we needed to find were this one, and this one. Really just x naught, y naught, z naught, because f sub x was given to be 2 and f sub y was given to be 4. Okay, so that was a tangent plane example. Let's find okay, so let let's change the color. Let f of xy equals x e to the y squared minus y e to the x squared. And then we have to find equation of tangent plane at 1, 2. This looks like a monster, doesn't it? A monster function. Well, okay, so what do we need? We need z equals z naught plus f sub x, x minus x naught, plus f sub y, y minus y. We have x naught, y naught. We can go ahead and calculate z naught, or f of xy. So this would be, so you're plugging in 1 for x, 1 e, 2 for y, but that's a y squared, so that's 4, minus 2e to the first. So this is just e to the fourth minus 2e. Okay, now let's calculate the partial derivatives for right here. Okay, so f sub x, well, this is x to the first, right? And this would be the constant term with respect to x. So we just have e to the y squared. This next one, this is a constant. This is my function. So I have minus, so this would be a 2xy e to the y squared. F sub y would be positive 2xy e to the y squared minus e to the x squared. Okay, and we're evaluating these 1, 2. Okay, so now we have, let's see, we have e to the fourth minus 2e to the first. Then we have 4e to the fourth minus e to the first. This should be a 4. It's a 4 because we have 2 times 1 times 2. We have 2 times 1 times 2, e squared or y squared. Okay. Okay. Tangent plane. Tangent plane is z equals, and then z naught, or f of x naught, y naught. We already calculated that. That was e to the 4 minus 2e to the first. Then we have to plug in f sub x for, that's like the normal vector for the plane in the x direction. E to the fourth minus 4e to the first. Then we have x minus x naught. X naught was 1. We just put 1. Now plus, and then partial of f with respect to x was 4e to the 4 minus e. Then we have y minus y naught, which was 2. So as ugly as that looks, that's the right answer. I mean, you could potentially, let's go ahead and do it. We could distribute this here and here, because this is just a number. This is also just a number, so we can distribute it here and here. So we have z is equal to e to the 4th minus 2e plus e to the 4th minus 4e x. And then this would be plus 4e minus e to the 4th. And then we get plus 4e to the 4th minus e times y plus 2e minus 8e to the 4th. What do we get? We have e to the 4th, e to the, oh, those cancel, don't they? Cancel, cancel. Let's see, we have e, we have 4e, we have negative 2e, it's positive 2e, the positive 2e that cancels all of these. And then we have the constant, so we have, okay, we have z is equal to x, well, that's right, e to the 4 minus 4e x plus 4e to the 4 minus ey minus 8e to the 4th. Okay, cool. Let's see, okay. Suppose we need equation of tangent plane to surface S at P1 to 213. You don't know, we don't know S, we don't know equation for S, but we know the curves both lie, we know these two curves, R1 of t equals 2 plus 3t, 1 minus t squared, 3 minus 4t plus t squared, and R2 of t equals R2 of u, different variable, is 1 plus u squared, 2u cubed minus 1, 2u plus 1. We know that these both lie on S. Find equation of tangent plane at P. Well, if we notice, our point is 2, 1, 3. If we plug in 0 to the first equation, so we have R1 of 0, we get 2 plus 0, which is 2. 1 minus 0 is 1. 3 minus 0 plus 0 is just 3. For the second equation, we plug in, let's see, 1 plus 1 is 2. 2 minus 1 is 1. 2 plus 1 is 3. So we plug in 1, we get 2, 1, 3. So these curves lie on the surface. They lie on the surface, S. They intersect at 2, 1, 3. And so if we take the derivatives of these two vector value functions and evaluate at this t equals 0 and u equals 1 values, then we would have two vectors that are parallel to our plane. Then we would only need to take the cross product of those two vectors to find the normal vector and then plug it into our plane equation to find the equation of the tangent plane without even having to know S. So if we take R1 prime of t, which is 2, minus 2t, and then we have the constant goes away, negative 4 plus 2t, and then we have R2 prime of u is equal to 2u, is that 6u squared to, yeah, just 2, okay. Yep, evaluate these at, so we have R prime of, R1 prime of 0 is equal to 2, 0, negative 4. That's wrong. Because this first function, this 2 goes away, and this is 3t. This is actually a 3. Then we have R2 prime of 1 would be 2, 6, 2. So we have our surface. We have surface. We have S. Oh, we don't have S. We have the picture of S, and then we have some curves, something like that. This is the point, 2, 1, 3. We're finding, what are we finding? The tangent, vectors tangent like that and like that. And we're taking the cross product of these two. And that will give us the normal vector at that point. If we do R1 prime 0 cross R2 prime 1, IJK 3, 0, negative 4, 2, 6, 2. This is I times, we get I times 0 minus 24, so positive 24 minus J times 6 minus negative 8. 6 plus 8, that's 14. Plus K times, let's see, we got, I cancel, and so we got 18 minus 0 is just 18. That vector is too big. Let's scale it down. I can divide by 2, so this is 12, negative 7, 9. It's as far as we can scale it down because it's 7. Okay, so now we're going to take our normal vector and dot it with x minus x naught. X minus x naught is x minus 2, y minus 1, z minus 3. Set it equal to 0. So we get 12x minus 24 minus 7y plus 7 plus 9z minus 27 equals 0. Now start collecting the constants. Okay, so 12x minus 7y plus 9z. See, this positive 7 and negative 27 is negative 20. Negative 20 minus 24 is negative 44. So equals 44. Okay. I guess while we're at it, we have a parameterization, don't we? Because these two vectors they lie on the plane, they're linearly independent. And then we have a point, so we have parameterization. I guess we have to call it R3 of ST is equal to our point, 2, 1, 3, plus s times 3 is negative 4 plus t times 2. So, we can scale that down, can't we? We can do 1, 3, 2. Yeah, so that's the parameterization. And then we also have the level set equation we just calculated down there. Cool. All right. Exactly when are we allowed to approximate complicated functions with tangent planes or linear approximations? When can we do that? So we're going to talk about the notion of differentiability. To motivate this discussion of differentiability, let me define a tangent plane more rigorously. So, tangent plane. Let F map R2 to R. Remember, this just means two-dimensional input, one-dimensional output. So it's going to look like f of xy equals z. This is a three-dimensional interpretation of a function. So let this be differentiable at x naught equals x naught, y naught. The plane in R3 defined by the equation z is equal to f of x naught, y naught, plus the partial of f respect to x naught, y naught, times x minus x naught, plus the partial of f respect to y, x naught, y naught, times y minus y naught. It's called the tangent of the graph of f at the point x naught, y naught, f of x naught, y naught. Cool. So, f must be differentiable to find the tangent plane. But what is differentiability? What does that even mean? What does that mean in the multiple variable case? We know what it means in the single variable case, I hope. If you've forgotten it, I'll remind you. So the limit of the difference quotient, right? We have the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So if this limit exists, then we say f is differentiable at x. Okay. I'm going to give you some equivalent statements now. So if we let h equal x minus x naught, then if h approaches 0, then that means x approaches x naught. And then plugging it into our limit of the difference quotient, we have the limit as x approaches x naught of f of x plus x minus x naught. Wait a second. Yeah, do it like this. X naught, X naught, X naught. So that way, when we plug in X minus X naught, the X naughts will cancel, and then just get f of X minus f of X naught over X minus X naught. And this is equal to f prime of X naught. So this is an equivalent statement of differentiability for a function of one variable. Now what happens, so this is just a number, right? This is an equation. So I can just subtract it over. And I'm going to say, okay, well, another equivalent statement is the limit x approaches x naught, f of x minus f of x naught minus f prime of x naught. Right, this is over x minus x naught. So I'm just going to multiply this by x minus x naught over x minus x naught. So I have a common denominator. So if this limit equals 0 now, because I subtracted the f prime of x naught over, if this equals 0, then we're differentiable. Now this happens if and only if this happens when the limit as x approaches x naught, the absolute value of f of x minus f of x naught minus f prime of x naught times x minus x naught over the absolute value of x minus x naught equals 0. I see the absolute value in. So let's move this to differentiability of another specific type of function, right? We're talking about differentiability and f maps, R to R. All I'm going to do is, give a definition of differentiability for f maps R2 to R. Okay, so the output is a real number. The input is two real numbers. So that's, z is equal to f of xy. So we say, okay. So we say, say a function f maps u, a subset of R2 to R, let u be open, is differentiable at a point x naught in u if the limit as x minus x naught, as the limit as x approaches x naught of the absolute value of f of x comma y, right? Because it's x naught, really x naught comma y naught minus f of x naught y naught. We have minus, well, what did we have up here? We had the derivative, which was a number. But this time, our x minus x naught is really a column matrix, right? Because we have, the two inputs. So this would be the norm x y minus x naught y naught which is really, we could just say this is x minus x naught for shorthand. And so we'll have, you know, some well, it'd be a matrix, right? Because to be able to combine this f xy, which is a number, with this f of xy, which is a number, with this x minus x naught, which is a 2 by 1 matrix, we would need to have a 1 by 2 matrix. And well, it's the derivative, right? It would be 1 by 2. Remember, because when we're doing matrix multiplication, right, 1 by 2 multiplied with 2 by 1, these have to match up, which is good, and the output would be a 1 by 1 matrix, which is just a real number, so it can combine with this 1 by 1 and this 1 by 1. Another giveaway, right, is that this is a absolute value, right, whereas this is a 2 norm. So if this limit equals 0, then f is differentiable, or differentiable at a point x naught equals x naught y and u if this limit equals 0 for right, and we know what d is, don't we? D of f x naught is equal to the partial of f with respect to x of x naught y naught, the partial of f with respect to y of x naught y naught, which is 1 by 2. And these are just numbers, right? Because we evaluate the derivative at a point, would just give us a number. So it's like a linear map, because matrices are linear transformations, if I'm not mistaken, or something like that. I don't know. But anyways, so this is the notion of differentiability. But I mean, you don't want to use this bulky equation every time. And I mean, in this class, you don't even really need to, you know this. But another equivalent statement to differentiability, right? This guy will happen if these derivatives, the partial derivatives, are continuous. The partial derivatives partial f respect to x and partial of f respect to y exist near and are continuous at x naught y naught, then f is differentiable. So I mean, you know, like all the functions that we've been running into up to this point, you know, for instance, f of x naught or xy is equal to x e to the y squared minus y e to the x. Well, like how we know this is differentiable is because when we took the partial derivatives, I mean, it was just a familiar function, a polynomial times exponential. Well, yeah, we know that's continuous. You know, but what happens if we get something that, I mean, it could be, we don't really know, right? What if we get some function, some weird function, f maps R2 to R, given by f of xy equals xy over x squared plus y squared. If xy do not equal 0, and it's 0 at the point xy equals 0, 0. So we're going to show that this is not differentiable because the partial derivatives are not continuous. So recall the partial derivatives, the definition is the limit as t approaches 0, f of x plus t, y minus f of xy over t. Similarly, never say that word, dude. In a similar manner, right, we fix x, and then we treat y, with the plus t. Small change in y, leave x constant. Right. Okay. So, let's calculate the part, because I mean, if we're not at 0, 0, then we don't really. I mean, it's going to be some continuous function. But let's examine at 0, 0. Let's examine the partial derivative. Let's examine the partial derivative of f with respect to x at 0, 0. This is the limit as t approaches 0, f 0 plus t, comma 0, minus f of 0, 0 over t. And we have our function xy over x squared plus y squared. So if we plug in 0 plus t, comma 0, this is really just t, comma 0. So this is going to be the limit as t approaches 0, f of t, comma 0, so that's going to be t times 0 over t squared plus 0 squared. F is 0, 0, right? It's piecewise defined to be 0 there, divided by t. So this is, what do we get? We get the limit as t approaches 0. This numerator is 0. This denominator gets absorbed down here over t cubed. And so this limit, right, is this is non-zero because we're taking it at the limit as t approaches 0, and 0 definitively on top, so this limit equals 0. So the partial of f with respect to x at 0, 0 is 0. It can also be shown for y, so we're going to do that with partial f with respect to y at 0, 0, limit t approaches 0, f 0, t plus 0 minus f of 0, 0 over t. So what do we get? We get 0 times t over 0 squared plus t squared minus 0 over t, the limit as t approaches 0. So we get the limit as t approaches 0 is 0 over t cubed, which is 0. So these partial derivatives both equal 0 at 0, 0. But let's go ahead and calculate f sub x for xy not equal to 0. What do we need? We need the quotient rule, xy over x squared plus y squared. So we get low d high, derivative of the high with respect to x is just y, minus high d low over the square of what's below. So this is x squared y plus y cubed minus 2x squared y, x squared plus y squared squared. This is y times y squared minus x squared over x squared plus y squared squared. Okay, so this is with respect to x, xy. And recall that a function is continuous if the limit equals the function. You know the function value f of xy, or f of the partial f with respect to x at 0, 0 is equal to 0. And so we're going to show it's not continuous at 0 by showing that the limit as xy approaches 0, 0 of the partial of f with respect to x of xy does not equal 0. So above here, right here, we're going to let x equal 0. And so we have the limit as y approaches 0, y squared minus 0 squared over 0 squared plus y squared squared This is equal to the limit as y approaches 0, y cubed over y to the fourth. The limit as y approaches 0, 1 over y to the third is equal to infinity, not equal to 0. Therefore, the limit does not exist. Therefore, the partial f respect to x is not continuous. And by that theorem, that tells us f is not differentiable. So any sort of tangent plane stuff that we do at the origin wouldn't work. The book, in fact, calls it too crinkly near the origin. Crinkly is the word they use, I think. Crumpled or something. We have some more time, dude. We have some more time. We're gonna talk about the chain rule. So I don't like how the book introduces the chain rule with those, the theorems in the box, because a visual picture works better for this. So if we have partial, we have w, the function of x, y, z, t. X is a function of u and v, y is a function of u and v, z is a function of u and v, t is a function of u and v. And then we want the partial of w respect to u. Well, you just follow it down. Here, take this path, take this path, take this path, take this path. Partial w respect to u, partial w respect to x times partial x respect to u, plus the partial w respect to y, partial y respect to u, plus the partial w respect to z, partial z respect to u, partial w respect to t, partial t respect to u. So you just calculate all that, and that would be your answer. So yeah, I'm gonna stop right there actually.